Hello everyone and welcome to Carlum Cymru revision sessions. This session this evening will focus on physics AS level and will be presented by Mr. James Ridd, A2 level, year 13, from Cynvig Comprehensive School in Bridgend. The session will last 45 minutes where James will revise circular motion topic. If you have any questions during the session, please use the question and answer section and we'll do our best to answer your questions. You will see that there's a hyperlink in the Q&A section. Please leave your name and email, and if you are interested to receive more information on future events. Today's sessions will be recorded and the recording and any relevant resources will be uploaded to the e-sgol website under the Carlum Cymru tab. Thank you, James Ridd, and over to you.
Thank you, Mrs. Owen. Hello and welcome. Again, it's nice to see you back at the Carlum Cymru sessions. As it was explained today, we're going to be going through circular motion. Now, circular motion, the first topic on the A2 course, is obviously involved with all things moving in circles. There's no surprise there. Now, I just popped a couple of examples here for us to, just think about. It probably pops up more than you might think, and it's probably worth mentioning that once you start looking for circular motion, you can see it in lots of different places. For example, you've got a picture of the London Eye there, and any kind of Ferris wheel for that matter is obviously an example of motion in a circular path. We've got a washing machine here, all right, and there is obviously within the drum of a washing machine as it spins, a lot of physics involved in circular motion there. And of course, as you probably be aware of, when a washing machine is on a spin cycle, maybe you're not aware, it depends whether you do the washing or not, I suppose. When a washing machine does the spin cycle, if it spins fast enough, you'll know that the clothes actually stick to the top of the drum as they go round, and there's a reason for that. We see it in nature, of course, in the case of the planets and how they orbit the sun, and furthermore we see it in how the moon orbits the Earth, and even on a larger scale how the sun itself orbits the center of our galaxy, the Milky Way. You encounter, of course, in things like roller coasters, and there's a lot of physics in roller coasters. It's important that they get this velocity right just here, right at the point here, because if you don't, then you've got some pretty significant problems and maybe a lawsuit on your hand. And then finally, probably a very scientific application. I don't know if anyone knows what this is. This is in fact a centrifuge, and this is a piece of scientific apparatus used to separate substances of different density, shall we say, whereby if you spin a mixture, then you will find, of course, that the heavier substances go to the bottom and the lighter ones will sort of stay close to the top. So it's a way of separating things, used in chemistry mostly. Okay. So on to then the content. So I'm going to take us through each of these, and hopefully we'll have a bit of time as well to do a past paper question or two at the end. So to begin with then, we're going to look at the terms, period of rotation and frequency. All right. So to start off with then, if we imagine a car tire, all right, a car tire, and we imagine a point on that car tire, then the time period would be the time it takes for it to complete one full rotation, right? And after it completed that one full rotation, that is what we'd call the time period. The time for one cycle, often referred to as the time for one oscillation. And it's a term that's going to pop up a lot on the vibrations topic, which is next, and simple harmonic motion. So, T then, or the period as defined here, is the time taken for one complete oscillation, often given the symbol capital T. Well, always given the symbol capital T, not little t. We should maybe highlight the distinction there. Little t could be any time, But when we're talking about big T, we're specifically referring to the time for one complete cycle of oscillation. Then finally, frequency. Well, frequency, as you'll probably know from year 12, is the number of complete cycles or oscillations per second. And the frequency can be derived quite simply from knowing the time period by that little formula which you'll have encountered in the past. So that's a little bit of a recap. Frequency is 1 over the time period, and frequency, as you know, is measured in hertz. Right then. So I'm going to say done for that. Now, the definition of the unit radian as a measure of angle. Now, at A2, we sort of go away from talking about angles in terms of degrees, and to some degree you'll have done that at AS already when you did the waves topic. We use radians in physics and in mathematics because in many ways they are a more convenient way of partitioning angles in a circle. I'll explain in just a moment what I mean by that. The definition of a radian then, if we imagine, again, a point in our wheel, all right, and we imagine that the distance it moves through, okay, is, or the arc length, right, which is this thing here, the arc length. When the arc length is equal to the radius of that circle, we can say that the angle subtended will be 1 radian. All right, so then if the arc length here is equal to the radius, which is here, then the angle here will be 1 radian. And that's our definition of the radian. So maybe I'll just write that one in quick then. So it's the angle subtended when the arc length is equal to the radius. All right. Now, the unit of measurement is just rad. All right, like so. And it's probably worth mentioning that if you were to come back here and ask the question, well, how many radians, okay, how many of these, all right, radians are in 1 complete circle? Well, because the circumference of a circle is 2 pi r, we know this, the circumference is equal to 2 pi r, then quite simply put, there will be 2 pi radians, okay, 2 pi radians in 360 degrees. So 2 pi radians in 360 degrees, you know, that means that pi radians, if you divide that by 2, is 180 and so forth. All right, pi by 2 would be 90, and then all the other different fractions thereof. So now we've defined what a radian is. Yes, we're going so fast. Right, to use the radian as a measure of angle. Maybe one other thing I just make a note of as well is that if you wanted to say what 1 radian exactly is, all right, 1 radian exactly is, because 2 pi radians is equal to 360 degrees, then 1 radian is equal to 360 divided by 2 pi. And I want to say that's 57 degrees. I'm just trying to remember now. How unprofessional of me. You work it out. 360 divided by 2 pi, I believe it's 57 degrees. So if you wanted a direct conversion of how many degrees 1 radian is, that's how you'd work it out. All right. I'm sure Miss Owen probably text me over the answer. Anyway, onwards then. We can tick this off as well as done. So now we're going to go for the definition. We're going to go point D now. So we'll just strike these off. We're on to point D now. The definition of angular velocity omega for an object performing circular motion and performing simple harmonic motion. I'm not going to go into the simple harmonic motion side of this in too much detail just yet, because that is in and of itself a whole other topic known as vibrations, which is the next topic to come. But we will nevertheless still define angular velocity. Angular velocity makes a lot of sense in terms of its unit measurement. It is, look, the number of, if you just look at the unit measurement here, it's the number of radians that an object will go through, all right, in a second or per second. So if you've got an object, again, let's just pick on the washing machine, maybe a pair of socks whizzing round and round and round and round and round, its angular velocity would be the number of radians it went through each second. Here's a top tip for working that out. Let's imagine we've got our, all right, there's socks now, okay? I'll draw a sock. Not a very good drawing, is it? Never mind. So let's imagine we've got a sock, and we think about how far it would go in one complete cycle. It would have traveled, wouldn't it, a distance which is equal to the circumference. So the angular velocity here is going to be, if you like, the angle it's gone through, all right, so omega, if it went through 2 pi radians, which is 360 degrees, okay, we said that. So if it went through a full 360 degrees, which is equal to 2 pi, like we said up here, all right, then if it did that, it would have had to have done that in the time period. Remember that one cycle, the time for one cycle we define as the time period. So if we know essentially how long the time period it takes to complete 360 degrees, then we'll know exactly what the angular velocity is. So that's radians per second. All right, radians per second. And this, of course, is radians, and this is seconds. So that's where we get our units from. Another important point worth mentioning is that we recall that F is equal to 1 over T. And therefore, we can also substitute this into the above formula, and I get another formula, which is W, or omega rather, is equal to 2 pi F. Right, so we've got these two formulas here. So those are our two formulas. Next, then, we're going to talk about now linear velocity. And I think I might just, I might just rub this out, oopsie-daisy, and start again for linear velocity. Okay. And linear velocity, I can just draw a circle, that'd be great. Oh, okay, it's a green circle, never mind. Linear velocity is all about, if you look at the unit of measurement, it's about meters and seconds. The unit of measurement's up here, look, right? It's about meters and seconds, just like any velocity measurement you've come across before. It's distance per unit time. So rather than talking about the rate at which angle is subtended, I feel like at the rate at which the angle changes, which is what angular velocity is, now we're going to talk about the actual physical distance an object moves through in a given time. So if I've got an object, again, moving in a circular path, okay, then in one complete cycle, how far will it have moved? Well, speed is equal to distance over time. The distance here for one complete circle or one complete cycle is going to be 2 pi r, which is, don't forget, the formula for the circumference of a circle. And then the time this would have taken is the time for one complete cycle, which is going to be 2 pi r over t. Now, the astute amongst you will notice that this formula is absolutely fine in and of itself, okay? But we've also just previously defined something which had 2 pi r, or so 2 pi over t. So if you look at just this little part here, right, that is equal to omega. So we can write velocity as v is equal to omega r. And that's another expression that we can use for calculating velocity. Here's an important result as well, right? I want you to imagine for me, if possible, that we've got, oh, let's, I don't know if you're even aware, There's a game that we used to play called Conkers when I was a lad. I'm quite old now, see, right? You wouldn't know what a conker was, probably your age. I don't know. Kids still play conkers? You tell me. Put it in the chat. But let's imagine I got a conker, and it's like a nut. Yeah, a big nut. On the end of a bit of string, you used to smash them together to try and break someone else's conker, and that was a load of fun. That's before, you know, PlayStations and such. Now, if you were swinging a conker round and round and round, then we could work out its velocity, obviously, using the formula that we just discussed. But I want to imagine now we've got a knot in the string, okay? And the knot in the string is about halfway along. And this illustrates an important difference between angular and linear velocity, because if you think about it, the radius to the knot would be maybe little r, all right? But the radius of the circle to the conker, let's call that big R. The important thing is that the conker and the knot would complete a circle in exactly the same amount of time. They're both on that string, one at the end, one halfway up, and they both get through an entire circle in the same amount of time. So they both go the same angle in the same amount of time. So that would mean that the angular velocity would be the same for both. Okay, so angular, well, same for both. However, because if you look here, V, all right, is, if you like, proportional to R, the linear velocity of the conker would be a lot bigger, because if you like, one is V is equal to omega little r, one is equal to V omega big R. So the linear velocity of the conker would be higher than the linear velocity of the knot, yet their angular velocities would be the same. Little distinction. Centripetal acceleration. Oh, should we just go back to our checklist a second? Yes, I think we're going to call this one done. All right, omega. Centripetal force, then, this is the one that we're on now. Okay, and we'll first of all talk about centripetal acceleration. An object can be moving, all right, with a constant speed in a circular path. It can be going around and around at a constant speed. That much is true. However, if you remember the difference between speed and velocity, velocity is a vector, and therefore, as a vector, it is defined as having both magnitude and direction. That's crucial, because at any given point on this object's circular motion, its velocity, okay, is going to be in different directions. And therefore, it must be the case that this object is accelerating. And acceleration, just to revise year 12, it refers to an object speeding up or slowing down, but it also refers to an object changing direction. And acceleration can also just cause a change in direction when there's no change in the magnitude per se. So we've got all these different velocities here, all right? Because we got this object moving in different directions. Now, the acceleration of this object is always towards the center, okay? So the acceleration is always perpendicular. We'll put that on as well. Perpendicular to the direction of the motion. There is a formula that is associated with this as well. And believe it or not, it is very hard to derive, and it's not something you need to derive for your A2 course. So we're going to skip through that bit and just get to the result. And the acceleration is equal to v squared over r. As a consequence, then, if you think you can substitute, remember now v is equal to omega r. What this means is we can substitute into this equation above. So we end up with a. Now, instead of v squared, well, v squared, look here, would be equal to omega squared r squared. All right. So if we just bear that in mind and then substitute this in here, then we get a is equal to omega squared r squared divided by r. One of those cancels with that guy, and we end up with a is equal to omega squared r. So we've got, two formulas for this, okay, for our centripetal. Some people say centripetal. I've heard that. Centripetal acceleration, potato. It's up to you. So remembering then that quite simply, Newton's second law is F is equal to ma. We can then derive centripetal force. Because if we know and have an expression for acceleration for an object moving in a circular path, then we can very easily then have a formula for centripetal force. So F is going to be equal to m, and this time we can take both formulas. We've got this one up here, this one here, right, and we've got this one here, which we can substitute, which we'll do now. So we'll have mv squared over r. Should probably done it the same color, but never mind. And we'll have F is equal to m omega squared r. Look at us go. I thought I'd just mention this while I'm here. Newton having so much to do with gravitation and having really established this mechanics, made a very interesting realization. Of course, the reason why the Earth is held in orbit about the sun, we know, is because there is a force of attraction, gravitational attraction between the Earth and the sun. And we know that that force of attraction is always, directly along the line of action between those two objects. So here, look, you can see that the force acting on the Earth is always towards the sun. As it moves in its circular path, the force is always directed towards the center, which is, of course, the sun. And therefore, of course, the acceleration is always towards the center as well. It's just a neat little way of illustrating that. All right. Later on in the course as well, you will be equating the law of centripetal force with the law of gravitation, Gm over r squared. Very important. This incredible result was derived from just messing around with that relationship, which I'm not going to go into now. I think I might have it on another video on the website if you want to check it out anyway. But moving on. So I think we can probably say now that we have, I think I'm happy. Well, I hope you're happy. The idea of centripetal force is the resultant force acting on a body moving at a constant speed in a circle. And then the centripetal force and acceleration are directed towards the center of the circular motion. We're going to take that up as well. To use the following equations relating to circular motion. So just to check now, we have derived that. We haven't derived it, but I told you about it. If you want to go read the definition, good luck. Or the derivation, sorry, good luck. We've derived that and that. So actually, we haven't used them yet, but we have done them. So that is essentially the basics. Although I am going to go on to some scenarios which you need to consider. First of all, I don't know what you'd call this problem really. You can, and sometimes I've done this for my students, you can get a bucket of water, and as you're quite well aware, you can swing that round in a circle at such a velocity whereby the water will stay in the bottom of the bucket. Now, the reason why this happens is all to do with centripetal force. And if you imagine the bucket at the bottom here, it has a weight downwards, mg, right? And of course, we have this mv squared over r upwards. And the actual, if you like, reaction force, or the total amount of support force, right, that will be pushing up will be the addition of those two forces. You've got the weight, which is always there, but additionally, you have also got this mv squared over r, which will have a reaction force, because remember now, for every action is an equal and opposite reaction. So you will have the force of the water, if you like, the pushing down. The circular centripetal force pulling the water up to keep moving in a circular path. But of course, that will have an equal and opposite force down. And what you end up with is a total support force equal to mv squared over r plus mg. All right, and that is also true if you're at the bottom of a roller coaster. Okay, if you're at the bottom of the roller coaster, you'll have experienced at some point you feel heavier, and the reason why you feel heavier is because not only are you having to contend with your own weight pushing into the seat, but you're having to contend with the fact that you're being forced to move in a circular path as you're in that dip, and as a consequence, there is an additional force causing you to move in that circular path, and a if you like, a reaction force caused by that. However, if you're at the top, well, here you've got a little bit of an issue, because if you're not moving fast enough, then, well, I guess, that could happen, which is sad times. And here, the support force acting on you for your seat is going to be given by mv squared over r minus mg. Okay, and essentially, these two forces are now in opposition. And in the very rare case where the specific velocity then at which you would fall out of your seat is given when you have no support force pushing you into your seat at all. And that happens when mv squared over r, the centripetal force, is equal to your weight. So you can actually work out the velocity here at which you would just about stay in your seat, or the velocity at which you'd be likely to fall out, because any slower than that and there wouldn't be enough support force or reaction force caused by the circular motion to overcome or be larger than the weight pulling you down, and therefore you would fall out. All right. One more sort of strange thing that pops up in exams from time to time is circular motion of I guess you wouldn't call it a pendulum. This is like the procession of a pendulum in a circular path. So you can imagine this thing maybe moving around in this direction, okay? Like so, all right? If we had such a thing, they might ask you to derive a formula which looks a little bit like this: tan theta is equal to v squared over gr. This comes in various iterations, but what we're going to do is I'm going to show you how to derive that formula. I'm going to show you how we get to that point. This object would have a weight downwards, mg. We've got a tension here and an angle theta. We can actually write a couple of expressions here, because this object moving in a circular path would have a centripetal force of mv squared over r, as we previously derived. Therefore, we can, make a couple of assumptions. The first one is maybe a simple one, which is to do with these two components here. Okay, this one and this one. And that would be to say that they must be equal. So if the object was to not, if you get any higher or lower, accelerate in the vertical plane, so to speak, it must be the case that t cos theta, because we have to bear in mind we need the vertical component of t in this direction. T cos theta is equal to mg. And we'd have to also then maybe write another statement, which is that t sine theta, which is if you like, this component here, t sine theta would also have to equal mv squared over r. Now, I'm going to just call this one equation 1 and this one equation 2. If you divide equation 1 by equation 2, you would have t sine theta divided by t cos theta is equal to, let's see, get this right the way around, mv squared over r, but we're going to divide by this mg as well, times mg. Now, you cancel that with that, and then just remembering from mathematics that sine theta over cos theta equals tan theta, then that would allow us then to sort of simplify this. These t's also cancel. You then end up with tan theta is equal to v squared over gr. Thought I'd throw it in because it's these other sort of edge case problems that can be really difficult in exam paper questions. So speaking of which, it's probably time now that we went on to some circular motion past paper practice. Okay, let's check the time that we're on. Yeah, we've got about 15 minutes, so let's see what we can get done. Right, a fairground ride consists of a large empty cylinder of radius 2.8 meters with its axis of rotation vertical. A person of mass 66.2 kilograms walks into the cylinder and stands against its inner wall. The cylinder is rotated around the axis when the rotation rate is 36.0 revolutions per minute. The floor is lowered, but the person remains fixed in place against the wall as if by magic. And everyone has a great time. And that's what this is about, isn't it? It's a fairground ride. Look at the fun this person's having. Hang on, hang on, hang on. There we go. There we go. So first of all, we're asked to define the radian. Do I have to write that down? I don't think I do. Look a little bit further back in the video. I'll say it in words. It's the angle subtended when the arc length is equal to the radius of a circle. Calculate the period of rotation. All right. So to calculate the period of rotation, first of all, we have to think, well, we have 36, okay, 0.0, and the 0.0 is important. They put it there. That's 3 significant figures, 36 per min. So in terms of how many we have per second, if we've got 36 per min, then quite simply, all we're doing is saying, well, is that, yeah, we've only got to do the period, isn't it? 36 revolutions per minute. There we are. So if we divide that, we do 36.0 divided by 60, we're going to end up with, if you like, how many we have per second. That's going to equal 0.6. All right. Now, this is seconds to minus 1. So actually what we've got here is 0.6 hertz. We've just worked out the frequency. The time period then is 1 over f. That's equal to 1.67 seconds. Okay, it's the time period. Easy to get caught out with that one. The speed at which the person is moving the circle, well, this is speed, not angular speed. This is linear speed. This is v. All right, so you know v is 2 pi r over t. If you like the whole circumference of a circle, how long it takes to one whole circumference, we get 2 pi times 2.8 divided by 1.67, and that is equal to 10.6 meters per second. All right. Nicely done. 3 forces act on the person. The normal contact force from the wall, N, the weight W of the person, and the frictional force NF from the wall. These are shown in the student's diagram. Let's just double check. They weren't lying. They are there. Okay. Explain why the values of N and F are approximately 2,600 newtons and 650 newtons respectively. So let's begin with N. Now N, annoyingly, okay, is really the centripetal force. If you look at the diagram here, N is towards the center, person is moving in a circular path. That force is the centripetal force, okay? So that's mv squared over r. That's equal to 66.2, which is the mass of the person, times 10.6 squared, all right? Double check that, yeah, 10.6 squared, all over 2.8. And that is equal to 2,634 newtons, which I always like to do this. I go, well, yeah, you know, approximately 2,600. So I'm showing that it's really about that value. So that's that first bit done. Okay. Next, then we got to show that this value of 650 is right. So F up here, so look where F is the friction. Now that friction there must be equal to the weight. It must be. All right, so we can simply say F is equal to W, which is equal to mg. So that's equal to 66.2 times 9.81, and that's equal to 649.4 newtons. And then you've got to check yourself then. Have I done too many significant figures? You bet I have. This is 3 sig figs. This is 3 sig figs. So as such, this has got to be 3 sig figs. So to 3 sig figs, look, this is 650 newtons. Right? Lovely job. Maximum value that a frictional force can take is mu n, where mu, I like mu as a Greek letter. Do you like mu as a Greek letter? I do. Do you know why? Because if you look at it, it looks a bit like an M and it looks a bit like a U. And that's why it's a mu. It's a bit like an M, a bit like a U. It's a mu. Look, I just made that up. It's got nothing to do, but it's true though, isn't it? It does look a bit like both. Show that the person does not slide down the wall, provided that mu is larger than approximately 0.25. Right. So what we'll do is we'll say F is equal to mu n. And then we're going to say, well, that's equal to 0.25. We'll use that value times 2,634. And then that is equal to 658.5, right, newtons. Now, if you look at this, this is greater than W, right? And then, well, that works, isn't it? So show that the person does not slide down the wall, provided that mu is larger than approximately 0.25. If we set that value to 0.25, then that force will be 658, which is larger than the weight, therefore the person doesn't slide. Student says that as the cylinder slows down, the floor will need to be raised to support the person when the angular velocity reduces below a certain value. Justify this and determine whether this angular velocity, if mu is a value of 0.45. Okay, so let's give a lot of information in that question. To start off with then, we're going to think of F. And again, this time now, we're going to use that relationship F is equal to mu n. So F is equal to mu times n. All right. N is equal to F over mu, which is equal to 650 divided by 0.45, which is equal to 1,444 newtons. Right. Now that we've got that, all right, we can start to solve for angular velocity, because what we can now say is that n, remember, which is the centripetal force, is equal to m omega squared r. And omega squared is going to be equal to, we just simplify this then, 144 all over 66.2 times 2.8. And that equals, and that's omega squared, don't forget, that equals 7.79. And then omega is obviously the square root of that, and that's equal to 2.79 radians per second. So let's just check we've answered the question. Student says that the cylinder slowed down. The floor will need to be raised to support the person when the angular velocity reduces below a certain value. Justify this and determine the angular velocity if mu, yeah, we've determined that angular velocity. So that is 15 marks, all right? Now we've got a couple of minutes, so maybe we'll just have a little look at the next one before we wrap things up. A car travels at a constant speed of 45 kilometers per hour around a curve in a road with a radius 80 meters. Explain why the car is accelerating. Now we talked about this earlier on. The car might well be traveling at a constant speed, but remember, velocity is a vector. It has magnitude and it has direction. So because the direction is changing and the car is therefore accelerating towards the center of the circle or the circular path, we can say that, you know, it is indeed accelerating because its direction is changing constantly. Calculate the angular velocity of the car in radians per second as it travels around the curve. This is an interesting one, nice little one to finish off because you've got to convert things here, right? So we know that it's traveling at 45.0 kilometers per hour. And, you know, really break it down, make it easy for yourself, right? So that means it's, well, first of all, 45.0. If I divided that by, 60 times 60, then I'd actually have its speed in kilometers per second. So that would be equal to 0.0125 kilometers per second. And then if we wanted this in meters per second, we'd have to simply, if you like, times by 1,000, wouldn't we? Right, and then we'd end up with 12, move the decimal place 3 places, 12.5 meters per second. That's a nice little conversion there. Calculate the angular velocity. Right, so we've got our v, if you like. That's v. The angular velocity, remember, v is equal to omega r. Omega is equal to v over r. So if we do 12.5 divided by the radius, which is 80, then that's going to equal 0.16. Oops, so sorry. We've just worked out angular velocity, so that's going to be 0.16 radians per second. And then last little bit, then calculate the acceleration of the car and state its direction. So we've got to look back to our formulas for acceleration. We've got two. We've got a is equal to v squared over r. We've got a is equal to omega squared r. Take your pick. I'm going to go for v squared over r. So a is equal to v squared. That's going to be 12.5 squared all over 80. And that comes out as 1.95 meters per second squared for the acceleration. Discuss how the application of science enables cars to travel safely around curves. Well, certain things help a car to travel in a circular path to produce that, if you like, centripetal force. The first and most obvious one is friction between the tires and the road. So having good grip on your tires is one. Having a good road surface is another. All right, so you get that frictional force between the tires and the road. But other things as well, keeping as much tire on the road at any one given time is really important as well. So stiffening up suspension allows a lot of tire to stay in contact with the road. That helps. Having the car's chassis to be very rigid also helps. So roll bars. and rigid shafts in the car will also help it to maintain good contact with the road and therefore produce enough frictional and ultimately centripetal force to carry on moving in a circular path at maybe high speed. Who knows? Right. Okay, I think that we have probably done enough here now, because this last one here now we can say, although there are many past paper questions to do and encourage you to have a look at them, we have now used those equations, nearly all of them anyway, in the past paper questions that we've just done. And I've just run over, so Owen, it's over to you. And all I'd like to say is thank you, everyone, and I hope that was informative, and I look forward to see you in our next video.
Thank you, James. I hope you found today's session useful, and next week's sessions will be at the same time and will focus on vibrations.